be talking about the Julia language. How many people in the room have ever used Julia before? None? Good. Okay, so then the novice introduction level will be good. I'll start from assuming very little knowledge. So there's several different ways you can get started. This is a PyData conference, so probably most of you have a Python Anaconda type environment already set up. If you've been using your IPython Jupyter notebook, it actually supports now that it's called Jupyter, it supports Julia as an alternate kernel language. So it should be pretty easy to get started. There's also, this was recently migrated from, it used to be juliabox.org, and now it's juliabox.com, but it's the same deal. If you don't want to install Julia right now, it's a not huge download, but if you want to just try this out in your browser, you go to juliabox.com, and you can use a Google authentication, sign in with any Gmail or anything. And this will run a hosted Docker container just on Google VM that will pop up in a few seconds, a hosted Jupyter notebook and console environment. So this is also a cool thing you can do without needing to set anything up. Or if you do want to install it locally, if you think you'll be using it more than just for this, depending on how convinced you are, julialang.org/downloads. So the stable release version is going to be 0.4.6, something like that. We're doing a release candidate for our next version right now, but for the purpose of this demo introduction, there's not going to be too much of a difference that you'll notice right away. So I'd recommend going with the stable version. Not all the packages are totally updated right now. But if you use Julia, so the main basic Julia installation gives you a prompt. It'll run in your terminal. It's a REPL. And you can install packages that way. So the way to interface to your Jupyter notebook is you do pkg.add iJulia, using iJulia, and then notebook. And that should fire up. If it already has Jupyter installed in your system, it should be able to find it, hook into it, and not need to do too much else. It should create a new kernel profile for the Julia kernel. And then locally you can open, it'll look familiar. But you'll be able to run Julia kernel backends. OK, so let me know if anyone starts going through this process and has any problems. We've got tons of time, and it's not too many people in the room. So. OK, so it's a PyData conference, and I'm not talking about Python. But why a new language, right? Julia hasn't been around for that long. It was only released open source in 2012. So it's a PyData, right? So presumably people have some sort of numerical problem you want your computer to help you solve. You're writing code to do data analysis, processing. So sort of my phrasing of this is, you have a problem to solve. If somebody else has solved a similar problem and has written code and shared their code open source, we use our tools wisely. We pick tools that are already available to give us a head start. It's great. Use their code. Libraries like NumPy, SciPy, Pandas. These are huge, great resources to start from to make your life easier, so you don't have to build everything from scratch. The issue is, what if it's not enough, right? You start with what's available, but then you need to do more, right? Is it easy enough to use? Does it perform well enough? Can you understand it? What if you need to add a feature, fix a bug, right? Can you modify the code to suit your particular use case? So conventionally, if you're good, if you're set, then thank the author, fix a bug, help out. But if not, the problem that Julia is sort of out to solve in conventional tools, especially classical Python, R, MATLAB, these conventional environments for doing numerical and scientific computing, is you have this two-language problem, as we call it. So this is just sort of a quick snapshot of the GitHub repositories for Python itself, NumPy, and SciPy, of what languages are they written in. So it's not the greatest measurement. This is, exactly how GitHub counts this can be a little weird sometimes. But you look at CPython itself is 40% C. NumPy is over half C. SciPy is a mix of Fortran and C and C++. And So there's a lot of low-level, nasty C code that a lot of people don't want to be writing in day-to-day or have to worry about when things go wrong. So you kind of have this user-friendly code you work with day-to-day that you want to write in something nice and high-level like Python, but then when performance is a problem, you have to go down to something lower level. Or there's this great flowchart that this may look familiar. I'm borrowing this from a Julia user named Helgi Eichhorn, who does astrodynamics, but if people can read this, this is sort of a decision tree of if you have Python code and you want to make it faster, you kind of have to go through this, is it numerical code, is it not numerical code, can you vectorize it, write it in NumPy, or try Numba, does it work, or Cython, there's all these sort of different tools you can use, and a lot of times you end up having to rewrite the most performance critical parts in C. So what Julia is out to do is make that unnecessary. So, Python, NumPy, SciPy, these are all very mature projects that have been around for a long time. But nowadays, it's 2016, there's a lot of advancement in technology, especially if you think about browsers. A lot of the development in making JavaScript run ridiculously quickly in your browser has developed a lot of advanced compiler technology, just-in-time compilation. There's a lot of the LLVM compiler framework, which is also used by Numba and Clang. If you've compiled C code on a Mac anytime in the last few years, it's using the LLVM compiler framework, which is open source and a very, very useful resource. So using a lot of these technologies that are available now, we know how to make a dynamic language that feels like Python run as quickly as if you were writing code in C. So this is possible today, and this is the goal of Julia. So if you go and look at the Julia repository, 2/3 of the code in Julia, just in that repository, is in Julia itself. So you can write the standard library, the basic operations of the language in the high-level language and still have it be high performance. So I'm going to spend the rest of the time in some notebooks. So these notebooks I'm borrowing from a professor named David Sanders, who's done a lot of really great tutorials. I'm trying to zoom in here, but so these are at github.com/dpsanders, and there's a set of them. So there is Invitation to Julia is one of them. Oh, okay. Well, I already have them cloned, but there's Invitation to Julia is one of them. Hands on Julia is another. And I think it is Intermediate Julia. Yes, okay. So I've already cloned all three of these, but so this is a very useful tutorial set of notebooks. They're all kind of, he's been developing these and giving tutorials over the last several years, so they're pretty closely related to one another, but this is what I'm going to be mostly working from, is sets of these notebooks. So where am I? Okay. So starting out, this was Invitation to Julia Part 1. So we're going to just start from a kind of motivating example of let's do something in this language called Julia that people in the room have not used before but are interested in finding out about. Okay, so this is your Jupyter notebook. And let's just say, let's do Newton's method, right? Basic kind of calculus, okay? So the Julia language should feel pretty familiar. There's nothing too crazy that will look out of left field if you're used to Python or other MATLAB or R or other sort of standard dynamic interpreted languages, right? So I'm going to set a variable x0. Some nice things that Julia, the fact that it's 2016 and Unicode is standard now. Python 3 has also done this now, as you can use Unicode in your variable names if you like making them look pretty and look like the math. So in Julia's REPL, there's a convenient shortcut to actually make these Unicode symbols easier to type. So if you've ever written a paper in LaTeX, there is the backslash notation for how to get a lot of these symbols, right? Backslash, if you're writing in Greek characters, \alpha or \delta. Okay, so Julia has tab completion for a lot of these standard mathematical notations for superscripts and subscripts with \, right? So you can tab complete on a lot of these symbols. Okay, so that's also a convenient, notational, make your code look a little prettier as be part of your identifiers. Okay, so in Julia is a dynamic language, but it's also a language in which you talk about types. So every value in Julia has a type associated with it. So we were giving this x0, we were assigning it the integer value of 4, which is, if you're on a 64-bit system, is going to be defaulting to a 64-bit integer. Okay? So now let's not just assign variables, but let's actually assign some functions. So Julia has a nice, convenient one-liner, very much like the mathematical syntax for defining a function, of saying fx equals x squared minus 2. And the function itself, I'll get more into what this means, this output of generic function with one method. I'll get into what that means. But the f is a function object. So functions are first-class values. They have a type associated with them. This will change, but type of f is function. So you can also pass these around. But if you want to call that f on the x0, on the value 3 that I had assigned to it earlier, pretty straightforward. Okay? And so we're going to be doing Newton's method as our sort of motivating example to start with. We're going to need derivatives of a function, not just the function, but also its derivative. And if you like your mathematical notation, you might want to use prime for that. But in Julia, prime is actually a special syntax. So prime, like in MATLAB, will be used for matrix transposes. So if you try to make prime on the left-hand side, that's actually going to be a syntax error. But as we were showing earlier with Unicode, this is something that maybe you would want to do and maybe you might consider is too hard to read. But Julia allows you to do this. You can use the Unicode prime character of doing \prime and autocomplete, and that's actually a distinct character. So that can be part of your identifiers and doesn't have a special syntactic meaning in Julia. So if we've defined f prime as our derivative function. You could also do this with superscripts, right? Superscripts don't actually have a mathematical operator meaning to them. You might think this would mean squared, but no, it's just the Unicode character for superscript 2. So this is actually, the variable name is x squared here. But the right-hand side, the value, the syntax, I'm taking x naught squared. Okay? Right, so one step of Newton's method, starting from 3. Right, I take the initial value minus the function divided by the derivative. Okay? So that was step 1. And you'll notice this is another sort of difference between Python 2 and Python 3 of what do you get when you divide two integers, right? So Julia follows the Python 3 convention of anytime you divide two integer-valued functions, or integer values, it will give you a floating point result by default. However, there is, if you want integer division, you can still have it, it's just spelled differently. So you can do div if you really need integer division. Right, so div, if you're dropping div 5 of 2 is going to be just dropping the remainder. Okay? So I've wound up going from integer valued inputs, integer valued functions, but because of the division, this result was now a floating point. Okay? So another thing to notice that's going to be distinct from Python is when you're doing integer arithmetic, it's going to be machine integers. So this is going to be, as we showed earlier, it's an int64, an integer raised to an integer power. And there's a function to look at the bit representation of, I took 2 to the 62. So you can see we have a 1 in the second highest bit. But if I then multiply that by 2, it wraps around. right? So this is machine integer arithmetic. It's going to be modulo 2 to the, it's going to be a signed integer, right? Because I multiplied by 2, the integer arithmetic shifted to the left, but that is actually now the sign bit. So I got the smallest value. You can also see there's functions for this called type min and type max. So this is the smallest value of the type int64, or the largest value of the type int64. This is 2 to the 63 minus 1. Right. So that's something to notice. If you want an arbitrary precision integer, Julia has that by default in the standard library, but you have to convert to it. You have to explicitly say, I want a big int type. I want an arbitrary precision integer. Right? So if I take a big integer 2 and raise that to the 62nd power, this is going to still be a big int. Same value, but then if I multiply this value by 2, so this is shorthand here, right? So Julia does support the shorthand modification in place. One thing to note is this always is exactly equivalent to writing this, right? So anytime you were to see times equal or plus equal, it's going to just exactly be equal to the operator, or the left-hand side repeated. So this is something that's part of the syntax.
How does that work across scopes, like with references?
So this is going to be it's going to be rebinding. So it's going to be as if you wrote, so I'll show arrays soon, but if I had, right, an array, y as an array, and then I wanted to do but now so z is still 1. Where'd it go? It's probably clearer if I so if you've done an array, you're actually going to be rebinding, right? So this is going to be exactly equivalent to if you had written y times 2. So the left-hand side is actually going to be creating a new array. Okay. And one thing to note is the big function, right? If you take it, this may look a little misleading, but it's actually just doing the exact same thing that we were doing earlier, where 2 to the 63 was in the integer, or the machine integer wraparound arithmetic. So this is actually wound up overflowing before I converted it to a big integer. So that's something to note, is that where you put the parentheses will matter in the order of operations there. Right? And with arbitrary precision integers, you can start doing, things that will take a while and give very, very long, very high precision integer arithmetic numbers. So this will use the underlying GMP C library, if anyone is familiar with that. But the nice thing is that Julia will give you these sort of high-level interfaces to it, so you don't have to worry about wrapping the C library underneath. Right? So this was a 19,000-digit integer there. Okay.
For these calculations, is there the equivalent of Python's timing?
Mm-hmm. Yes. So the normal way would be using the macro at time. So that's the standard way. We in the default standard library, we don't actually have, I think in Python, the timeit macro or annotation or whatever it is will by default run it multiple times and give you an average and a little bit of statistics. We don't have that by default, the time macro, the at time macro in Julia will only run things once. So you will notice if you were to run some big long running calculation, The at time the first time will actually include the compilation time. The second and third and fourth time will reuse the already compiled code. Julia, as I mentioned, is just-in-time compiled. So the first time you call something, it might have some compilation time overhead. And the time macro doesn't hide that from you. Okay, so in terms of iteration and loops, right? We were just dealing with simple scalars. So far, Julia has for loops, while loops, standard control flow that you would expect. Right, so in Julia is not indentation sensitive. We use end to mark the end of blocks, which can kind of help if you're not in the notebook, if you want to do a one-liner, right? If you want to do for I in 1 to 5, you can just squeeze it all on one line if you really feel like it. The semicolons here are necessary if it's all on one line, just to demark where the expressions end. But here, we recommend if you're writing code that you plan on reading ever again, indentation is for humans. There's a style guide, but it's not enforced by the language. You can still parse ugly code if you want. Okay. So one thing to note is that the iteration variable I is actually only defined inside the loop. Okay? So I don't have a variable I after I've run this loop. It was available inside, but it's scoped in that way as a local variable. Okay? So I was using the colon notation. I was using 1 to 5. So that is a range object. All right, so if I ask Julia, what is the type of that 1 to 5 object? So there's several built-in range types that use the convenient colon syntax to create them. One thing to note, as you probably saw, is that in Julia the ranges are closed, right? So they're inclusive of the endpoint. So this goes with, it's kind of connected to the way in which you index arrays. Often they go together. Julia takes the one indexing, counting as if you're counting. You start, the first element of the array is 1, and the last element of the array is n, if it's n elements. So the ranges are closed. Okay. So you can go from this 1 to 5 is a unit range object, right? And it's going to be a type that's defined in Julia, and it's also going to have some fields. I'll get into. So this 1 to 5 is going to be a unit range object that will actually have a start and a stop. So this is going to be stored compactly, just in terms of its start point and its end point. So it won't actually, if you've ever written in MATLAB or R, I think when you do a for loop over a range, it actually constructs the dense vector of every single element that it has to visit, just to know that I'm iterating over a for loop. Julia uses an iteration protocol. So this 1 to 5 is an iterator, an iterable object, and you can convert that into an array with the collect function. Okay? So if you want to take an iterator and say, give me an array of what each successive element in that iterator would have held, you use collect to do that. Okay? So collect will give you an array, right? And by default, the array is going to be a dense, possibly multi-dimensional array of values. And you'll notice the curly brace syntax, so that is a type parameter. That is telling you what the element type is. So here, because the start point and the end point of this unit range were both 64-bit integers, every element in the array is a 64-bit integer. So this stores a lot, this does a lot of the essentially efficiency optimizations that NumPy does, where NumPy is able to be efficient on homogeneous arrays where every element is the same type. In Julia, that's just built into the default array type. You could have an array, if you start with just an empty array with just brackets that doesn't have anything in it, then Julia doesn't know what the element type is. So that's going to be an element type any, and this will be much more like a Python list. right? Where any element could be, you could have a string in the first element, and then an integer, and a floating point, and it would be heterogeneous. Okay? But if you're collecting a unit range of integers, then you're going to get an array of integers, where the element type is all the same. Okay? Right? That was 5 elements long. Right? And we could also, construct arrays. It'll look pretty standard using square brackets. And you can iterate over the elements of an array. So arrays are iterable, so you can use this in syntax. You could also use the equal sign. So either syntax is accepted in a for loop. I think if you want to get into Unicode, sometimes we can use this is not implemented yet in Julia 0.4, but in Julia 0.5 it'll accept this in a for loop if you want to make your code look even more like the math. We do accept that in a containment, right? So I can say, is the value 4 in the array W? And I get, yes, 4 is in the array, right? And I can also do the Unicode version of that.
Can you use equal like that?
In for loops, yes, right? So in the for loop, you can. But outside of the for loop iteration specification, if I was to say 4 equals W, no, that's not right. I can't assign to the integer 4, so that's an error. Okay. So now we have loops and we have basic values, so we can actually do Newton's method. All right, so we had the function f, we had f prime, its derivative. We start from x0, 3, and we'll do 10 steps. We'll say x new is the starting value minus its value, the function value over the derivative, and we'll print. So println is a function that will print a set of values you give to it, followed by a new line. If you don't want the new line, if you wanted it all on one line, you could do print, but that's a little harder to read. So we'll put in some line breaks with println. So that's going to say the I value, the tab character, \t if you're the escaping of the tab, and then the new value. So I started the first step after 3. X0 is 3, x1 is 1.83 as we had seen, and in 10 steps it converges pretty close to the square root of 2, which is one of the roots of this function, right? But if I were to give it -3 as the initial condition, you can see it's going to converge to a different result, right? So let's look at a variety of initial conditions, right? So we'll say this is another way of specifying ranges. Here I'm saying the step of this range, right? So this is going to be a floating point range that starts at -5, goes by 1/8, and goes to 5. So that's going to end up with 81 elements. So of course, if you're in your notebook, then tab completion is very useful. The Julia REPL also supports a lot of these things too. If I wanted initial conditions equals whatever. So the basic command prompt, you don't have to use iJulia if you would rather work in a basic prompt. Oops. So the tab completion and all these things also work there, outside of iJulia. Okay. Or if I want, so that the default showing of an array, if you have an array of thousands and thousands and thousands of elements, you don't want the spam of every single element necessarily, at least not by default. So it'll truncate. It'll show with some ... saying that there's more elements in here, but I'm not going to show them all to save your output. But if you want to show them all, you can use the show all function for that. So that'll show absolutely everything, but in a one-line form. So this we had done is a different type now, right? So this is going to be now a float range, and the elements of that are going to be float 64. Okay. All right. So in the curly braces, that gives you the parameter of this type. Okay. So if you want to make an array, another way to do this, you can create an uninitialized array using the similar function. Right? So initial conditions we had was a float range, and we used collect as one way of creating an array from it. Another way would be similar, which will not copy the values. It will just create an uninitialized empty container of the same size, but the values in it will be uninitialized memory garbage. So don't read from these. This is just for writing to. So this is whatever happened to be in memory. It's going to be different every time. A lot like if you were using C malloc, right? You can't rely on the values that you get there. It's just an uninitialized container of a given size. Okay? So there's some convenient iterators to do certain patterns. So one of these is called enumerate. So if you do enumerate of an iterable object, here this float range, how that works is that gives you a counter and the value, right? So it's equivalent to what I just commented out here of saying for an index j from 1 to the length of the array of the iterator, and then saying at each iteration I want to take the jth element of the iterator. So enumerate is just a convenient shorthand for doing that. And it returns a tuple, right? So in parentheses is a tuple of the index and the value. And you do destructuring assignment on the left-hand side. So this is the way of assigning multiple values. So I can say if I want a comma b equals, so this is something that I think James was also mentioning as being some extensions to this are relatively new in Python 3, extending interesting ways of doing multiple assignments and destructuring. Julia supports that as well through tuples. And enumerate, yeah? Not on the left-hand side. Or actually, sometimes no. Yeah, so that will give you, so not always. I think the parentheses I find a little more explicit sometimes, but you can leave them out when the context is clear. Right, so if the parser is able to figure out that that's exactly what you meant, then you can leave them out. You mean if I had a tuple of, what do you unpack in what way? Yeah. So that is, oops. Oh, here. So that is done with the dot, dot, dot. All right, so that printed 4 and then 5. Okay. So I have enumerate gives you the tuple of the index and the value, a counter and a value, which just saves you a little bit of boilerplate when that's a common iteration pattern. So now I'm writing into the array roots, right? So we created this uninitialized roots array that we were going to write the results into, and here we assign into the jth element of the array with the value that we got after here 100 iterations of Newton's method.
Do you have to give a size of an array when you initialize it?
Yeah, so you do need to initialize it as some size, but if it's one-dimensional, you are allowed to actually grow it. But you use a different syntax for that. So unlike in MATLAB, if you were to write beyond the end of an array, MATLAB would grow the array, which is one of the things that makes knowing what size an array is going to be in an intermediate iteration kind of complicated. And I think it will lint at you and warn you if you do that, if it's able to figure out and tell you this is going to be slow. But if you want to grow an array in Julia, so the way you would do that, so you can create, so I was creating earlier an empty array. So this is an empty array of any, but you can create an array with a particular element type by giving the type to the left of the brackets. So this is going to be an empty array of integers. And then if I want to append an element to the end of that array, you use push. And there's a convention in Julia where functions that end in an exclamation point, this is really just a naming convention, but it's pretty common in Julia to want to do in-place operations. So the exclamation point is a convention that means this is going to be mutating one of its arguments in place, usually the first argument. So here push is saying that it's a mutating operation. So the value that A has before is going to be mutated after the function is called. It has side effects.
Is that appending to the head or the tail of the array?
It's at the end, right? So if I think there is a way to append at the beginning, and I think that's called unshift. Right, so I started empty, I added 6 to the end, I added 7 to the end, and then I added 1 to the beginning. Right? But because I declared the array as an integer, if I then want to append something that's not an integer, you'll actually get an inexact error. So Julia will not change the element type of the array. It will give you an error if you try and put something in it that doesn't fit. But it will try to convert. Right? So if you give it a floating point number, but a floating point number that is exactly convertible to an integer, it will do the conversion to put it into the integer array. But it will give you an inexact error if it's not exactly the same value. Okay, so we were showing enumerate, right? So enumerate of an array of integers, and just looking at what that successively does. It does the counter, 1, 2, 3, and then the values of the iterable object that you give to enumerate. Okay? Right, and as I mentioned, tuples. So the parentheses. If you want a tuple with only one element in it, you actually do need the comma to disambiguate. If you were to give just the parentheses, that's just the integer 3 in parentheses. So it's a little bit ambiguous with the one element tuple. So a single comma tells you that it's one element, but the empty tuple is just empty parentheses. All right. Okay. All right, so after we had done, So we had assigned the roots to all of the initial conditions in that array. And we saw, essentially, for negative initial conditions, we wound up at negative square root of 2. And for positive initial conditions, we wound up at positive square root of 2. Right, and if we were to look at all of them. One interesting thing is to note that at exactly 0, we end up with a nan. That means somewhere divided by 0. And that's not going to be an error in the normal 64-bit floating point arithmetic. If you divide by 0, you'll end up getting, you'll end up getting infinity if you divide by 0, but then if you start doing operations with infinity and 0, then you'll quickly get a nan. Right, so this is IEEE 6754, standard floating point arithmetic rules. Okay. Right. So, and you had asked the time it macro. So the time macro will tell us how long this takes. So one thing you will probably be surprised. You thought Julia is supposed to be fast, but if you take a look at this, this was only doing. Okay, what was this doing? 10,000 iterations, and the number of allocations is a little crazy. So this allocated over a gigabyte. And the reason for this is everything we've been doing so far has been in global scope. So these have actually all been global variables. And in Julia, it makes a really big difference to performance. So a lot of times people will try Julia out, try porting some Python or MATLAB code to Julia and run it and say, this was really slow, and complain on the mailing list or something. And usually the first thing that happened wrong is everything was a global variable. And the reason Julia is able to be fast, which I'm going to get into, is inferring the types of variables and compiling that to efficient native machine code as if you were writing in C or Fortran or a compiled language. Right? So if Julia is able to figure out what the types of everything are supposed to be and knows that they're going to stay predictable, then it's able to compile efficient code transparently. But if things are global variables, then you can't make any guarantees. Because it's a dynamic language, you can change the value, you can change the type of a global variable. Right? So I have, right, the global variable A, if I wanted it to be an integer, and then I wanted to change its type later to be a floating point number, Julia lets you do that. It lets you, the value that you give to A can change if it's global. So you need to be able to provide some guarantees that the type doesn't change and do some analysis and inference. And this is sort of the compiler's job. If you are writing in a compiled language, then to make the compiler happy, you would need to make sure that things are declared types and stay consistent types. In a scripting language, in an interpreted language, the interpreter would have to check every time and say, is this a floating point number? Then do floating point operations. Is this an integer? Then do integer operations. And in Python, everything is a Py object. So every single operation that happens on it needs to dispatch and do a potentially different operation each time. So that's part of a lot of why you learn that for loops very quickly in Python and MATLAB are slow, and you have to vectorize things and use libraries like NumPy. So you're sort of taught not to write Python code with explicit for loops like this. You're taught to find a vectorized way of expressing your operation or use a library. So the way around this, which I guess is not in this notebook, but so there's a very simple, you put it in a function. Right? So earlier we had the one-liner, right? Earlier we were doing fx equals x squared minus 2 or whatever. So the longer form, if it's not a one-liner function, is you spell it out. So if it had input arguments, you would do arg1, arg2, etc. But a zero-argument function just takes no inputs. So if you put everything in a function, and then if you want it to return a value, then you can say return roots. Or the return is implicit in the last statement. So the last expression that gets evaluated, if you don't write return explicitly, that will be returned. All right. So if I then do, and there you can see the allocations were much smaller. Actually here, this was actually probably the allocations from compiling this function. So that was the first time I ran it. It had to compile it, and it just did that for you. The second time you run it, no, okay. So the compiler overhead was not actually that much. I was expecting it to be more of a difference, but the first time you run something, it will actually be getting compiled, and you'll be measuring the compilation time. But you can see how much of a difference that made versus this version. Right, that was like a 20 times difference and way more allocations. So here, everything is a global variable. In the function form, the Julia compiler is able to realize that you've defined all of these as local variables inside the function, and it's able to track and say, did you change the value? Did you change the type of these variables within this function? No, you didn't. This stayed a range. Great. You don't have to worry about it being something else. In the global variable case, you might change it later. So you need to be conservative. Okay. So this was 20,000 roots that I just calculated. So there's a lot of different ways of plotting data in Julia. Nothing is built into the language by default yet, but there are a lot of external packages. Most commonly, people will use matplotlib in the Python world. And there's actually, hopefully I'll get to it, there's a very, very good way of interfacing into Python libraries from Julia. So if you have a lot of Python code that you already use, and you want to sort of not have to rewrite all of it, then Julia actually makes it pretty easy to use your existing code in your existing libraries through a package called PyCall. And I'll show some examples hopefully soon. But one very good example of existing Python libraries and code that you might want to use is matplotlib, right, to plot data. So the pyplot Julia package is a Julia interface to matplotlib. Okay? Right, and just showing, right, so I haven't done any strings yet. So in Julia, you use the double quote for string literals. So that's an ASCII string, and I mentioned earlier Unicode. This is something that's going to change. In Julia 0.4, ASCII and Unicode strings were different types. In Julia 0.5, now everything is just going to be Unicode by default. So the package manager is built into the Julia, and you can use pkg.add to install registered packages. So there's a list. There's about 1,000, a little more than 1,000 registered packages that are available in Julia right now. We need to come up with kind of a better way of making these more discoverable so you can figure out what's worth using and what's unmaintained. But the pkg.julialang.org is just a dump alphabetical listing with a little bit of a summary. There's also a page that will sort of list what are they, which packages are being actively updated, which packages have the most GitHub stars, what's trending, what's passing their tests and what isn't. So given a particular Julia package you might want, like I just told you about pyplot, if you don't have it installed already, you do pkg.add pyplot, and it takes a minute. It's built on, the package manager is built on Git. So all of these, pretty much all of the package repositories are on GitHub. And you'll notice when you add a package, it's actually cloning it through Git. So if you're not comfortable with doing Git on the command line all day, you don't have to actually do that. So the package manager in Julia sort of gives you, just wraps around Git for you, so you don't have to worry about all the particular invocations to make Git happy and do the right thing. It will just manage the versions for you. Okay? It also manages, you're not always on master of these packages. You're using release tags, and they have interdependencies and requirements. So there's a way that the package manager knows what dependencies the graphs package has or pyplot has. So for example, pyplot, if you were to install it on JuliaBox, for example, then it's going to find out that these are all the packages that pyplot depends on, right? So I mentioned particular pycall, right? So in order to interface with Python, it needs pycall and another set of packages to do the plotting. Okay, so that's an annoying error message that we'll hopefully figure out how to fix. That wasn't supposed to happen. But anyway, so excuse me. I have a whole bunch of packages installed. By default, they'll go into a .julia directory under your home folder. And then under the version of Julia that you're using, I have a whole bunch installed. You can also use pkg.status is another way. So pkg.status, yeah.
There's like list or installs or something.
Mm-hmm. Yeah. So, okay, so what that was doing, so remember how I had shown when you have a really long array, it'll truncate the display and won't show absolutely everything. So it will do that as well for other collection types. So this will take a minute, but so I have a whole bunch of packages installed on my machine, and this has to read a bunch of information from the disk, which is a little slow, particularly because I'm on Windows at the moment. But what that's going to show, pkg.installed is going to give you a dictionary. It's going to be a hash table from package name to package version. So it'll give you a list of however many packages you have installed, and from string of the name to version number type of the installed version. And the truncation is really just not displaying it all, but they're all there. So you can I'll show you actually since we just mentioned them, I'll show you what hash table types look like. That's a useful type. Right? So I'm going to say, so this is the syntax in Julia for defining a dictionary type, a hash table. Right? So you give it a set of pairs of keys to values. Right? And then once I have that, I can access the values indexing with the keys. Okay? And you can iterate over them as well. So if I say, what are the keys of the dictionary D, that'll give you an iterator object, and you'll notice that the keys are not ordered in a hash table. So the order in which you get them is not necessarily predictable. And the values will also give you an iterator of the values. Right? And you could turn that into an array if you want with collect, but you can't necessarily rely on the order. So the package.installed, if that's done, there it is. Yeah, so that was the dictionary from string to version number. And let's say, I think I have PyCall installed locally. Yeah. Right? And because Windows kind of sucks at Unicode, the ... is a funny symbol. Yeah, so we're going to try to probably ship a better terminal emulator that actually can do, if you use Cygwin or Git Bash, those are better at Unicode and can actually show the characters correctly. Okay. All right, so I had shown the difference between defining a function in which you do everything, in which case Julia is able to know that these are local variables, and because it hit the end of the function and you didn't change their types, it's able to compile efficient code for them. No, okay, I don't have that many packages installed in Cygwin. So. But you'll have to trust me. Or I could do the VDots. Nope. Bad font. Okay. Unicode and Windows. Okay. So I had added a couple of these packages, and you can do using pyplot. So there's several different ways. Mostly two. So if you want to load a package, you can either do using the package, or you can do import the package. Now, in Python, it would almost always be import, and then in Python you do oftentimes you end up doing as, right? You do import numpy as some short abbreviation. We don't have the aliasing yet in Julia, but if you want to look, pyplot is a module. So if you really wanted to, you could do that, and then you could do all of the elements in pyplot. But usually, since you can almost always do tab completion, the aliasing isn't too big a deal. So using will take the exports of the package, which is sort of the definition of what is the public API, what are you supposed to use, and using will import those into your namespace. So those will, you'll now get a plot, right? So if I ask, where does plot come from? Right, so plot came from the PyPlot package. So we had seen this before of generic functions and methods. So every function in Julia is generic over its input types. Because values have types, and in Julia you talk about what the types of elements are, or you can, because it makes a big difference to the compiled code. You can also define methods for the same generic function. And this happens a lot. So let me skip ahead a little bit. Yeah. So this happens even for the very basic built-in arithmetic, right? So if I want, say, the absolute value, right? The absolute value of, right, -5, right? So that's just a built-in function, but there are many, many, many different methods of the absolute value depending on what input type you give it, right? So each of these are defined in a different location, and you can, in iJulia, it'll give you a nice little link, and you can see this is the Julia source code that defines the absolute value of a float64 input. Here, this is actually kind of one of the built-in operations. This is the interface to low-level, very low-level code. This is a pretty primitive operation, but a lot of other things, most other things in Julia, like this isn't a public function, but you can see the definitions. I mentioned that 2/3 of the language is written in Julia. You can open up the standard library and see how everything is implemented in Julia code. Right, and it's pretty simple to read. So these are all different methods for different input types of the same function. So these are all part of absolute value. It's all called abs, but depending on what input type you call it on, it dispatches to a different method. Okay? So if you were to call the absolute value of a diagonal matrix, that's defined here as a diagonal matrix of the absolute value of the elements, and on many, many, many different input types. Okay? Where was I? Okay. So when I did using PyPlot, if you ever want to clear out, if you want to reset the value, reset everything that you've done, workspace will clear things out, and it gives you a bunch of warnings, but you can ignore those. So now, if I just do import, then plot will not be defined somewhere. There we go. So ignore the warnings, but undef variable because plot is not defined, because I did import PyPlot. You have to do using PyPlot to get the plot method, the plot function from the package into your namespace. There. Okay. And a year or more ago, it used to take a very long time to load packages, but now packages get automatically pre-compiled the first time you use them, and then the saved compilation information, it will cache the compiled code. So the second time on that you load a package will be much faster in loading time. Okay. So if I'm going to use PyPlot, all right, so I cleared my workspace, so of course I don't have anything that we did earlier defined. All right. I even cleared, of course I cleared F and F prime at the very beginning. So f prime and f there. Okay. So now I have the 20,001 roots that I calculated, and we can plot them. And we get it inline in the notebook if you're using iJulia. If you were using the standard terminal, then I think this would pop up in a browser window, I believe. Okay. So yeah, as I described earlier, don't use global variables if you care about what the performance is going to be. Right. So just by putting the calculations in a function, they're no longer global variables, and the performance is much better. This is another thing here. So if you were to refer to variables, you actually don't need them to be defined yet. Right? So if I define f as the input times a, but I don't have an a yet, if I try and call it, then it doesn't know what a is. But it let me do this definition without complaining. So it didn't complain at compile time. It only complained when I tried to execute the function at runtime. So that was a runtime error and not a compile time error. In Julia, compile time and runtime kind of tend to blend together a little bit. But if I define a global variable a now, then I can call that function. So you have sort of late binding of global variables. Okay. So this version here, this is returning multiple values. Right? So previously I was just returning the results, the roots, but here I'm saying both the initial conditions and the roots. So here, this is equivalent to doing a tuple of the return values. This is how Julia does. Julia returns multiple values as a tuple, but you can leave the parentheses out, and it'll do the same thing. You can even leave the return out, and it'll be implicit. So here, this gives the tuple of the first return and the tuple of the second return. And I could even, I could assign those to two different results. Then, then A would be that first value, and B would be the array. Well, that's interesting. Oh, I know why. Because I redefined f. I shouldn't have done that. X squared minus 2. There. So this was, really? So that was returning a tuple of a float range and an array. Okay. So whose is a convenient way of getting all of the names that are currently in your namespace. This is the packages that have been the modules that have been loaded. Base is the standard library. And then all of the local variables and functions that you've defined. Right, we had defined some of these arrays, some functions, some ranges. Okay. Okay. So what we've done so far wasn't especially interesting. We really weren't doing anything interesting with the inputs. It wasn't very generic. We just tailored it to that specific case that we were running. We saw that if we then redefined f, it kept giving errors. But you could make a more generic function, a more generic version that would actually take the function and the derivative function, the evaluation and the derivative, as inputs. Right? So this is going to be much more generic. Now, by saying I want to do the Newton method roots with the function and the derivative provided externally, now I can use this on many more cases. Okay? So this, now I've defined another method. So every function is generic, and I've given another method to this do roots. The first version that I did several inputs ago took no inputs. The second input took 2 inputs. Okay? So depending on how many inputs I call it with, it's going to dispatch to a different version of the implementation that I wrote for the same generic function name. Okay? So now, if I call this version with 2 inputs, and this is another one of those things that is going to, that we actually fixed. This was essentially a bug that when you pass functions as inputs to other functions, Julia used to not be able to optimize that very well. But in Julia 0.5, which is coming out now-ish, that is now fixed, actually. So this is going to be much better for the higher order programming and passing functions around and still getting high-performance code. So you might not always want to give functions names. You might want anonymous functions. And the syntax for doing that in Julia is using the arrow. All right, so I take the inputs to the anonymous function and the value that the anonymous function returns. And you can make it a multiple argument anonymous function by doing a tuple of the inputs, right? So a tuple of input arguments to maps to kind of result of the function. So this is a very, convenient syntax. I think in Python it's a little bit more verbose. You have to like write out lambda. Could be worse. It could be Java, but Julia makes it really compact to do anonymous function definitions just on one line.
So currently, could you pass anything to do roots as long as it's 2, but it doesn't have to be functions, right?
Right. So because we didn't actually annotate the types here, we just gave them names, but we didn't give them types. So we could try to put in an integer. What's it going to do? So if I try and call do roots of 1 and 2, so it is calling this version with 2 arguments, but this error message, at least on Julia 0.4, it got up to here, and it tried to call an integer as a function, and it said that I don't know how to call an integer on a floating point number. And that will also look a little different, but the error would mean the same thing. As a consequence of the way in which making anonymous functions and making functions as arguments fast, the way in which that was implemented means the error is going to look a lot different, but you can't call an integer as an object, right? It's not a callable object. You could define, if you have your own custom types, you could define what does it mean to call that type. Like, for example, I can call, right, int is a type, but I can call int on, if I call int on a floating point number, right, that will try to convert, right, and give you an exact number if it's exactly convertible, right? So this is what calling, if I call an int, then that works, right? So if I call, actually that's probably going to give also an error, but what is that going to do? So that's going to say, it's actually probably just identity. I think if you call float on an input that is already a floating point number, it's just going to be the identity. So that's not a very good derivative. So I think this is nonsense. It took 1,000 iterations of subtracting 1, I think, which is not very exciting. But yeah, so if you don't annotate the types of a function, then it can take anything, but it might not be meaningful. So if I want to say,
I'm sorry, I'm going back a little bit. So when you were saying that version 5 is better than that was with respect to inline functions. So the second method now where we have a generic do roots with the passive function derivative, that's not the one that's slower. It's the next one where you have the inline, the lambda function, right? Anonymous function.
it's both, but to different extents. So both are faster now. I think we did I delete that call already? Oh, here, right. So you can see this still allocated a bunch of memory, and usually that means it can't figure out what the type is, and it has to make it any and do dynamic dispatch at every iteration, which means it just needs to allocate a lot of memory for the potential values it might contain. It's boxed.
How do we annotate them? You said that we
Yes.
give a hint?
Yes. So this is the idea behind dispatch. So if you annotate the function arguments with a type, right? So I could say, right, this wouldn't be very meaningful, but let's actually do something more simple. So if I want to say A, B equals any, okay, then I want to call, right, so far, okay, that was any. I haven't done anything interesting. I only defined one method. Right, so that was just dispatching between the number of input arguments. But you can also start saying new methods for specific types. Okay? So this called the generic A because the input was an integer. But if you call it on a floating point, it will dispatch to the method that's defined for floating point inputs. And the idea I've mentioned a few times of multiple dispatch is you can do these in arbitrary combinations. All right. So that was any. So you can see all the possible different combinations you might define. So saying that you're doing the same generic function, the same verb, but for many different combinations of input types. And this actually ends up being really convenient for sort of mathematical operations on things that are sort of like a number but have different behavior depending on what particular variation they are. You can imagine the particular implementation, like I had shown early on, arbitrary precision integers, right? If I want to add an arbitrary precision integer to a floating point number, that is going to look very different in the way you implement that than adding, two floating point numbers together or doing some calculation on those input types. If you actually want to make it, if you actually want to do the very low level, right? If it's a big integer, if it needs to call some library, then I need to do some C interfacing. And you can imagine that the method body is going to need to be very different. Okay.
Does it matter? With the annotated function, it still allocates 1.1 memory gigabytes.
Right. So annotating types actually does not make a difference for performance. Annotating input types of functions really only does dispatch. So that'll tell you which implementation to call when the inputs are that combination of types, but the Julia compiler already knows what types they were. So when you called the version without any annotation, right? So if you did the version with no you didn't talk about types at all, when you call that for a particular combination of input types, the Julia compiler will compile it for that combination. So the end result in terms of the performance you get is not any different. So annotation is just for dispatch and potentially for documentation, right? If this only, this, as we showed, this didn't actually make sense for integers. So we might want to annotate this as saying, hey, this only makes sense when f and f prime are functions. And then if that was the only method, so do roots annotated. Right, so then if I tried to call that new version, if I've only defined a method for function inputs, if I try and call that on integers, it's going to say, I don't have a method for do roots annotated on 2 integer inputs. So you might want to do it for sort of self-documentation of consistency, that this code doesn't do anything sensible for types other than some subset. But the performance is going to be inferred by the compiler anyway. So the actual combinations of input types that it gets called on is what it's going to get compiled for. Okay? So this was walking through basically the same thing, right? You'll note if you call, you haven't talked about types at all here, but if you call it on an integer versus you call it on a floating point, it's actually going to have to compile different methods. It's going to have to compile different implementations for taking the square of an integer versus taking the square of a floating point number. Those are going to end up needing different native code implementations. You don't have to see that, but Julia actually lets you, I might be skipping ahead a little bit again, but one thing that's very interesting about Julia is it lets you ask the compiler what it's doing. So there's a couple of macros you can use for this. So here we had this h of x is x squared. So you can ask with these macros, code lowered, this will sort of give you the internal representation of what the Julia compiler represents that function call as. This is kind of hard to read. You don't really need to, and it doesn't actually, it just says return x squared. It wasn't that interesting. Code typed will be a little bit more interesting, and that will say, okay, I called it on an integer, right? So when I did so here, this did not have any type information. This was saying the x input is any. So I'm calling it on any, doesn't know any type information. Code typed sees that you're calling it on an integer 3 and knows, okay, I'm calling it on an integer, then I can dispatch that x squared will actually get transformed to x times x. So I think there's a inlining pass somewhere in the Julia compiler that recognizes x squared is often more efficient to replace with x times x. So that's what it's done here. So it's done integer multiplication of x times x, which returns an integer result when you call h on an integer. If you were to call it on a floating point number, then it would be floating point multiplication. Okay. So, and the dispatch goes to the most specific matching combination of types, right? So if I did hx is x squared without a type annotation, but then hx for float x is x cubed, then you end up getting very different results, right? So this is something that you probably don't, this could be pretty confusing of getting very different results, whether something is an integer or a floating point number, even if they have the same value. Sort of part of the justification for dividing two integers, right? We had, that Python made that change between Python 2 and Python 3. You probably want the behavior of generic functions to be relatively consistent. Otherwise, it should probably have a different name, just for clarity's sake. Okay. So I think I had shown, right, absolute value earlier. Complex numbers, syntax for doing that is IM, built in as the imaginary unit. Right, so that, oh geez. Good, okay. So you can see that was of type complex with integer elements. But then if I were to do, right, floating point, then it's a different type. Yeah, right. So the abs of a complex number, you can even see where it's defined, calls to hypot, which is defined, I think that calls into libm. You can actually see. You can also ask which. So if I do the hypot function that I saw this calls, it takes the hypot of real and imaginary elements. Then you can use this which macro to see, okay, which particular method is going to get called there. Okay? So here, what this is actually saying is promoting the types. So in order to get them to the same type. So these definitions are a little bit different. So this says x could be any real number type, y could be any real number type, but real is what's called an abstract type, which is like a particular super type of multiple other subtypes. Right, so abstract types do not have any values. You cannot have a value that is an abstract type. An abstract type is just a grouping of similarly named concrete implementations. So for example, you can ask, there's a subtype operator, right, that says integer is a subtype of real and floating point is a subtype of real. So the abstract type real will take values of either. Right? So for dispatch purposes, any subtype of real, but they don't have to be the same subtype. So if I were to call it with an integer and then a floating point, it would call this method. But this method here is saying if x is of type t and y is of type t, with the parametric constraint that t is a floating point number for both of the inputs, then it dispatches to this method. And this is a method, actually, okay, so this does not call libm. This is actually in Julia. It's saying the absolute value of x, the absolute value of y. This is swapping, saying if x is smaller than y, then swap them so that they're always sorted. So this is just a particular combination of steps to make sure you're avoiding overflow. You want to do things carefully to get the right answer if one of the elements is really, really large. The naive way is just say, square this one, add them, take the square root. But if that were to overflow, you'd get a nonsense answer. So this is just being careful about that case. Okay? Right, and so there are some things that people have implemented to work around the fact that anonymous functions were also a little slow, but if you start with Julia 0.5, you don't have to worry about it. Okay. so what the results that we got, couldn't really see much from that viewpoint, that zoom level. But if I look between 1 and 3 on the x-axis of where interesting things are happening, you can see that function had some interesting behavior. Okay. All right, so I think the next step this goes into is extending this to complex numbers, where Newton's method starts getting more interesting. It ends up with some pretty pictures in the end. This is actually showing you that even multiplication, so even infix operators, are actually generic functions. So they're just pretty syntax for calling, right? You can call multiplication as a function if you want. And it's going to be, so the normal infix syntax is equivalent for infix operators. So even basic operations like multiplication, this is telling you all the 100-something different specializations, specialized implementations of multiplication that have been defined for all sorts of different combinations of types in the standard library. And then if you were to load, you can see here at the end, because I've loaded a few extra packages, then packages will also start defining their own types. And like here, there's color types. And this package has defined multiplication between numbers and color types. So you commonly want to extend the built-in functions on types that you define in your own custom code as data structures for whatever custom operation you're doing. Okay? So I think let's actually go to speaking of types. So there's two different, you can either make a mutable container composite type or an immutable type in Julia. So the syntax for that is you name the type. If you want it to be a mutable container type, you can say type, whatever the type name is, and then you give it fields, right? So this would be field 1, this would be field 2. So Julia, the types and the methods that are defined on them live sort of separately. It's not really a conventional object-oriented language like Python or C++ or Java, where you have classes that define both the data structure and the behavior on them with member functions. In Julia, the types are just the data structure, and the methods define verbs, behaviors to operate on them. So you can define types, custom types, and you can also annotate the fields. So if you want to say the fields should have some particular types, then the syntax for doing that is as follows, right? So that would define an immutable type with one floating point element, or a mutable type, a composite type with three fields. Okay, and by default, when you define a type, it's going to have constructors that are defined for it by default that are going to sort of do the obvious thing. So I just said this is the data structure layout, and the kind of obvious things to do with that are if I want to make one of these, I want to construct one. The default thing is it's actually just going to say, if you call it on something and it had that one field, right? The vol was just wrapping a float 64, and it's just going to convert that to a float 64. If you try to call it on a string, it's going to say, I don't know how to convert to a float 64 from a string. So that won't work unless you were to define a particular constructor. If I wanted to do that, I could then define a type, define a method. Excuse me. So constructor methods to create a type are functions that have the same name as the type itself. So if I want to say, if I want to define a constructor method to make one of these objects from a string, then I could say so this is the syntax for taking a string and parsing it into a float64. You do as you do here. All right, so now that I've defined that, now I can call, oops, whoa, I didn't want to do that. Sorry. Now that I've defined that method, that works, right? All right, so that was saying the constructor for a string input, which was not one of the ones that was defined by default. The default constructors are saying, okay, if you call it with the type that it should be, that's the easy case. And if you call it with anything else, it's going to try to convert by default, which might fail, as we showed earlier. As we showed, when there wasn't a specialized method, if conversion failed, you weren't allowed to construct it. Here. Right.
Could you go back to convey that? What was that conversion? If for some reason you didn't want it to accept this.
Yes. So there's a difference between constructors that you define outside the type and constructors that you define at the definition time. So there's inner constructors that you define inside the type declaration itself. And you could say, you can do either declaration syntax with these. Here you could say, right, can only construct. All right, so then, if I were to so then the methods of that type. Let's actually define it from scratch. Let's define a new one, just to be sure. Right. So this does not have the default. So that overrides. I was actually supposed to, oh, there, that's why, because I didn't have the names matching. There we go. So that was the inner constructor that I just defined. So you can be pickier if you want in the constructors that you define. Okay. And since we declared this as an immutable type, you're not allowed to mutate the fields. Right? You can't assign to the fields of an immutable type. They are construct once, and then you can't change them. So this is useful for allowing the compiler to do cleverer things. If it knows that you're not going to be able to write new values, then it can actually turn field access. Right? If it's only ever going to have the value that you assign it at construction time, then anytime you look up this field element, you can actually, you know that the value is going to be the same, which the compiler can take advantage of. Right? And there's several different syntax. So you can do v.value, or you could use getField, either by name or by index. Okay. So if you had used type, then you would be allowed to assign. I think I had shown. Okay. And now, if I want to do m.v1 and I want to change it to something different, and see what you can see that it actually allows you to set the value, right? So there, anytime you were to look up the value, it actually has to look up in memory to say where is that stored and get the value because it might change over time. But when you define your custom types like this, if all of the fields have well-known concrete types to them, then Julia is actually able to optimize operations like this very efficiently. So types that you define in your code, as long as they're structured in a way that the compiler can reason about, Julia can generate efficient code. There's no real difference between types that are built into the language versus types that you define in user code. So I think even the built-in types are actually defined in Julia, and there's nothing special about the Julia code that we wrote versus the Julia code that you write outside. So like complex numbers, for example, right, I think. So that's supposed to be a link. There. Right? So even the built-in complex number, this is saying that complex numbers are a subtype of the abstract number, right? So if you want it to be, if you want dispatch to work when something is declared to be a number, because a complex number is a subtype of arbitrary numbers, you define it, when you define the type, you declare it to be a subtype of the abstract. So you can actually make your own, you just do abstract, and then you can start defining subtype relations anytime you declare new types. So that's just used for dispatch. And then here, this is parameterizing to say that the real and imaginary fields of a complex number both have to be subtypes of real, and they have to be the same type T. But this is just Julia code, so complex numbers are not special. You could define them yourself. Okay. Right, so something to avoid, I said, if the types of the fields are something that Julia can reason about, it can generate efficient code. But if you don't annotate the types, then Julia has no idea. It's any, right? If you don't give an annotation, then it's just equivalent to saying, I don't know anything about what type it was. Any is an abstract type that contains anything. So then you could construct it with anything, right? So if I can construct objects with no constraints whatsoever, but this is going to be pretty bad for performance. This is basically going to be the same as if you had global variables. It's not going to be able to optimize. So here, this is what you actually want to do. This says that for any particular type of the value field, you put it in a type parameter. And this is making a family of types. So this is like templates in C, for example, generic programming, where you're declaring that the vol type is parameterized over the element type T. So the built-in like array types and complex types all do this to say there is a distinct type layout, right? If you were to have a complex number, right, or even just this type that we just declared, right, the parameters are going to be different. And the representation is going to be different as well. So when you do dot value here, it knows, because the element type is parameterized to be an integer, the Julia compiler is able to figure out that this field access is always going to give you an integer, and this field access is always going to give you a floating point. Whereas if you had not declared that type parameter, then it wouldn't be able to say anything about the types. Okay. All right, so this is what I had mentioned with abstract types and subtype relations. Right, integer and floating point are subtypes of real. There's a arbitrary precision big float type as well that you can use. But complex is not a subtype of real. And actually, I think because subtyping does not always work, so complex numbers are sort of a supertype in the mathematical sense of real numbers, but the type system in Julia can't exactly represent that constraint, right? The real numbers are complex numbers with imaginary part exactly equal to 0, but that's not exactly what the subtyping means in Julia. So that's what number was the parent of both. Okay. So if you want to impose constraints on the parameter, then when you declare the type parameter, you say it must be a subtype of a particular abstract type. And then if you were to declare it, right, because string string is obviously not a subtype of a real number. So if you've declared that parametric restriction, then you can't convert from a string to anything with the subtype of real. Okay? And this, where you had been asking, can you be more picky about the types? You can also be more picky about the values, right? You could say if you don't want to accept negative numbers at construction time, then you can throw an error when you construct the value. Although constraints like this are harder to enforce for a mutable type. So if you were to do, so you could do a mutable type version of this, and that would be fine. Is that right? Because I didn't tell it. There we go. So I actually needed to tell it more specifically what I was constructing. So here, it will throw that error and say, the inner constructor checked the value, but it won't check if I then change it. Right? Because this was mutable, I could then do, right, I could change it and make it no longer satisfy the condition that the constructor was trying to enforce. Okay. So you can then, of course, extend. You've declared these types, you've imposed a bunch of constraints on what they're allowed to contain and what they aren't. You can start defining operations on them, arithmetic. So if I've constructed, let's go back to the simple one. Nope, I think I want the even simpler one. There we go. Okay, so if I construct two of these types and I try and add them together, it's going to say, I don't know how to add two of these because there's no built-in definition for that. Okay? So the way to define that is you first import the operator. You need to do this to extend addition. Otherwise, if you try to just say, I'm going to define addition, parameterized over t, to say that if I'm adding two two values that are of this vol type, where the t parameter is the same, the value of that is a vol wrapper of the value of the first one plus the value of the second one, right? So this will actually give you a warning that if you try that, okay, so it will work, but you're supposed to actually import it first, right? So in order to extend, I think if this wasn't at the REPL, if this had been in a package, it wouldn't have worked at all without the import. So this is saying, otherwise you might be overwriting. So if I was to say, so a module is like a namespace. So most packages are built as a module. So this is like a grouping, a named grouping of types and functions and constants. So, and I want immutable vol. Okay. So if I did that, it's going to give me that same warning. Okay. Well, I was expecting it to give me an error, but I'm not predicting the way it's going to behave at the moment. Right. Okay. So if you've defined a method of the generic function addition for that combination of types, then you can start doing operations on it. So I think I don't have that much time left. I think this is supposed to end at 5. So I actually should get into some more like fun interoperability. So we realize that you're not going to rewrite all of your code in Julia. You have a lot of existing code. There are a lot of existing libraries out there. I showed briefly using matplotlib through this pycall wrapper. This is doable in a lot more interesting ways as well. So you can call into C libraries very, very, very easily from Julia. And the way you do this is very simple. So there's a built-in function called ccall, and the way you use ccall is you give it the function you want to call in the C library, and then potentially the library name, right? So if this was the sign, if I want to call the C sign function, then on a Unix system that would live in libm. We actually have a open libm that we use. We build it as a separate library. So you give it the function name and the library name, the return type, a tuple of the input types, and here sign just takes a single floating point, and then you give it the list of inputs, right? So this was me calling the C sign on the floating point on the Julia value here. And you can do this for much more interesting functions as well. So this is actually how we define a lot of these operations that are built on these libraries. So I had mentioned the big float is built on this MPFR particular C library. And the way this is actually just calling, it's using the ccall function, and it's saying the function name is MPFR underscore sine or cosine or tangent in libmpfr. It returns a status code that we ignore. So in this particular case, it's a slightly more complicated signature. Here it's saying I'm taking a pointer to a big float object as the output and the input, and then a rounding mode. And I'm giving it a pre-allocated output and a pointer to the input. And that's how we do sine and cosine of big float types. They're actually calling into the C library, but because of this wrapper code, you don't have to worry about how the C library works or what this signature is. You write it once, And you can even do this in a loop. So here we're looping over all of these function signatures. A lot of these C libraries happen to have very sort of uniform copy-paste signatures that appear, they're very, very closely related to one another. You can actually use just generic Julia code of I'm going to define these function signatures using C-call in a loop, which makes it much, much simpler to wrap huge C libraries when the API is really uniform. And this is actually what the PyCall library that I mentioned uses. So the PyCall Julia package just invokes the Python library to do the same thing that the Python interpreter would on a block of code. So I'll show a cool example. Right? So if you've done pkg.add pycall and you do using pycall, it has some convenience macros. So it has a PyImport, and this sort of imitates the Python syntax. So macros that I didn't really have time to go into, but macros allow you to sort of do arbitrary syntax manipulations by manipulating the expression tree of the Julia syntax. So it allows you to sort of define custom syntax extensions if you want. So scipy.optimize as SO is not Julia syntax, but the @PyImport macro knows how to read that and does something special with it. So if you have scipy installed and you do PyImport scipy, and then I call, this is me calling the scipy Newton method from on a Julia anonymous function with Julia values. Oh no. Oh no. Okay, so this is going to be exciting. Yes, yeah, so there's a Julia, so because SciPy and NumPy and Jupyter and everything can be kind of hard to install reliably without using Conda, we actually have we used to say manually install Conda first and then point to it to use all these Matplotlib and Jupyter and SciPy and everything. So now we actually just wrap it automatically and say we leverage, there we go, that worked, cool, okay, that was easy. So yeah, so this is me calling SciPy's Newton method on a Julia anonymous function. And you can see the result that I get of cosine of that value minus 3 times the value is pretty close to 0. Of course, this was pretty simple. You know, Newton root finding is very simplistic. If you're interested in numerical optimization, that's actually an area in which Julia packages are probably even better and more capable than the Python packages for advanced problems that have constraints and linear programming, nonlinear programming. I can talk your ear off about it if you're interested. But so that was a simple example. But you can extend this, and that's what the pyplot package uses. The pyplot package is doing importing Matplotlib and putting Julia wrappers around them. And PyImport is wrapping with C-call to call into Python as a C library to do the same thing that the Python interpreter would do. Okay, so I only have 5 minutes left, I think, and that's probably less time than you might have questions for. So I'll let people.
Any questions?
What is the best place to learn more?
Hmm?
What is the best place to learn more? I guess these are pretty static tutorials.
Yeah, so there's a set of resources that I think we have on the website. I think we have a learning page that has, so there have been a few books published, and there's also a good set of tutorials. So there's, and of course the standard documentation, which when I first was looking into Julia, I actually found the manual to be more readable than I thought it was going to be. And that's, I guess, just under the documentation. So I found the manual relatively readable and easy to get going on. I think, as I mentioned, the fact that the standard library is written in Julia means it's pretty easy to find your way around. And I think I contributed my first patch to Julia like a week or two after I first ever used it. So this is not uncommon. So yeah, either the manual or sets of tutorials. There are resources available.
It seems like there's still a lot of changes going on in the language itself. Like, would you say that it's ready to be used in production, or is it more still like something to be used experimentally?
So it's getting there. I mean, it's not 1.0 yet. We're in release candidates for 0.5 right now. We will probably have a 1.0 release within the next year or two. But we do, there are people who are using it in, it's best for sort of local experimentation, kind of data science interactive type tasks. But there's really nothing preventing you if you're adventurous and if you want to try things out. We've had a lot of people just tell us that just the productivity and performance gains that they wound up getting by starting to use Julia really just outperformed their previous systems by orders of magnitude, and it's taken over. It's small but growing.
How would you integrate this with like a web application?
So, I mean, there is a Julia web organization that has a set of packages for doing, HTTP servers, HTTP requests, WebSocket interactions. I think one of these is a package for developing, deploying a Julia application as an HTTP API. So these things are out there, and a lot of, like Julia Box that I showed you is actually built on a lot of these things. So they work. They're not quite as widely used as a lot of like the core basic like linear algebra type NumPy, SciPy type features that are right now in the standard library that come by default. But we're working to sort of decouple things over time and make the core language smaller in order to sort of have a lot of other things out in libraries. Make it more of a general purpose language. Python doesn't come with NumPy by default. A lot of people use NumPy all the time, but it's not really part of the language. And the way Julia technically is anything that is written in Julia code technically could be in a different repository. It could be a package, and there's no real technical difference. So there's essentially any way that you would deploy any other interpreted language, scripting language. I think Julia, something that will be developed further over time would be pre-compiling, like statically compiling Julia code into standalone executable binaries. Right now, that's not an easy thing to do. But that kind of works. Like the standard library is a shared object. It's a little harder to do for your user code, but we build a DLL or an SO or a dilib of the standard library code. Packages right now, the precompiled packages that I mentioned are not native code yet, but we probably will make that work pretty soon. Okay. Well, I think I'll be around for probably the next couple days if anyone has any other questions or wants to know anything. So thanks.